All right, Christine, can you hear me?
Yes, I can, Jeremy.
All right, well, good morning, everyone. Thanks for joining us. Let me see if I can get my attendance list up to make sure that I'm not seeing an attendance list. Do we have folks with us, Christine? Boom, there it is.
Jeremy, we've got about 54 attendees on the line.
Beautiful. All right, thanks everybody. My name is Jereme Gaeta. I'm a senior environmental scientist with IEP and CDFW, and I'm going to be the moderator for the next 3 sessions where we are doing a set of micro trainings. And I'll talk about that in a moment, but just a reminder, since this is virtual, we're doing everything a little bit different this year. We do not want speakers or attendees to continue chats on to the next talk, just so we don't have too many distractions. We also don't want the speakers to answer talks in the chat, or sorry, answer questions in the chat. I will go ahead and read the question to you, or you can read the question, or as an audience member, if you raise your hand, I will do my best to unmute you and allow you to ask the question yourself. So again, thanks for joining day 2. And this year's training is going to be a little bit different. In the past, what we've done is we've had half-day or several-hour workshop trainings where we're all in a room together, staring at fishes or staring at our laptops. And this year, as you know, with the virtual conference, we're trying a different approach. And I'm going to be reaching out to you all for some feedback to see whether or not this worked. But what we are doing today is we are going to have 12 15-minute talks, and these talks have companion materials that are going to be at the website down below. I'll be entering this link into the chat throughout the morning and the afternoon. But at this website, you will be able to download some sort of a handout. Varies with each speaker, but the handout is going to have basically a written version of what you're going to see in the presentation today. It'll come with a companion R script that you can upload onto your computer with a companion data set, and you can actually walk through the analyses that all the speakers are going to be presenting today. And then today itself, the presentations, like I mentioned, are going to be about 15 minutes with 3 minutes for Q&A, plus or minus. But if you don't get your question answered, or if you have a longer question and you don't want to try to squeeze it into those 3 minutes, after our last talk today at 1400 or 2 p.m., we are going to have 20 to 40 minutes, depending on how many people join us, of open Q&A, where we can answer any unanswered questions. You can bring new questions. You can even show up with data or a stats problem. And all of our speakers are very knowledgeable today. And so I'm pretty sure we'll be able to answer, at least point you in a direction. Now, I wanted to start by talking big picture, and the way that we have designed today's micro training is basically a wish list of what I wish I had when I started grad school. And this doesn't mean this is just for new scientists. The materials we're going to be covering today also have some very advanced topics that if you've been analyzing data for years, you still will learn something. But when I started grad school, I was a bit of a field monster where, I was working, I just got out of the Bering Sea and I was working about 80 hours a week when I was in grad school. And I made the silly mistake of going to my major professor, who's a renowned modeler, and saying, I'm not really much of a statistics person. I really just want to be in the field, and I really just want to learn how to do the best field work I can and how to be a really good field ecologist. And my major professor, who at the time and still is way smarter than I am, kind of smiled and chuckled and gave me a data set and said, why don't you read this book? I think you should look into that. And I saw the word model in the title, and I immediately was terrified. Back then, I viewed models as this scary black box where I didn't know where to start. I didn't understand the pathway. And I immediately started to kind of bottle up and found myself leaving that meeting not understanding my major professor's smile. But he knew stuff that I didn't. Specifically, he knew that every day, every one of us model all the time. When we use the word model, all we mean is a simplification of reality. when you, every week, or your partner, when you decide to go to the grocery store, you come up with a mental map as you walk in that grocery store of where to go and what to get. In your mind, you don't see every box of cereal, every apple. You just see the things that you need. Perhaps a better example of a model that we all can relate to, because we've all tried to write one and we've all used them on our Google Maps, is a map. In this case, we have the part, at least, of the run course from this year's Ironman. And this is just a model, again, a simplification of reality. Now, me as a grad student, when I first started, I would have thought, when I was building a statistical model, that we needed to add more. We needed to add all the information. We needed to have those runners in our map. We needed to have every single tree that they're going to walk through in the park or run through. Because we're in a city, we need to have all the cars. And of course, because this is America, we need to have about 1 million Starbucks on our map. Now, as some of you probably remember, this year's Ironman didn't go so well, in that it was actually rained out and severe warning caused it to stop. So when you look at these two images, these two maps, they both have the same goal, trying to convey the running path. The one on the bottom is a much closer picture of reality. We are just throwing information at it, and that makes it so much less useful than the map at the top. And so I always found this as a good understanding of how we can take this kind of scary idea that is modeling and help us kind of move towards a clear pathway and really take out the fear. And so what we're hoping to do today throughout our 12 talks is to not only give you a pathway, not only tell you how to start, but also give you tools that you can go back to, that you can reference, that you can continue to use to help you on your journey as you learn new analyses, improve the analyses that you already run, or just start from scratch. So today, there's a number of tools that we hope to provide. Specifically, we want to give you some kind of guide as to what analysis you should be performing depending on the data set you have and how to perform those analyses. And those are two things that I'm going to talk about next. But then for the rest of the day, we want to give you references. We want to give you materials that you can go back to. That includes the presentations you're going to see today, the handouts that are on the website, and then all the code and examples with data that are also on that website. So let's start with this what and the how. I'm going to walk you through a conceptual model that I built earlier this year, or late last year. With COVID, it's always kind of hard to tell, of what I wish I knew when I started grad school. Now, this is by no means the definitive pathway of how to do data analysis. This is just a useful tool to get you started. Now, generally speaking, there's kind of three main groups of analyses that are commonly used. The first is up in the left corner here, where we have categorical predictors. So predictors are what's on the right side of your equation, your X variables, and your response is what's on the left, your Y variables. We also have situations in which our response is categorical. What do I mean by categorical? That's just different factors, high, medium, low, site 1, site 2, site 3, species 1, species 2, species 3. And then the final common set of analyses are when you have a numerical response and a numerical predictor. So let's talk about how I would walk through this kind of dichotomous key, this framework. The first step that I always think about is, what are my predictors? Are they continuous or are they categorical? If they're categorical, how many do I have? Do I only have 2 or do I have more than 2? If you have more than 2, you're moving into this ANOVA or Kruskal-Wallis. If you have less than 2, you're in that t-test or rank sum. Now, these all should be analyses that you're common with, or at least you've heard of or you've read in a paper. Where it starts to get more complex is when we're looking at when we have non-categorical predictor variables. One of the first things you have to ask yourself is this a linear, sigmoid, or a linearizable relationship? Or is this a hump or some squiggly pattern? If it's not that hump or squiggly pattern, then you can move forward and start thinking about your response variables. If they're categorical, you're moving into this class of analyses, where arguably the most powerful, and again, it's not limited to just these types of data, but this is a really good tool, is going to be your classification tree. Now we can move forward to the kinds of analysis that we're probably all really familiar with seeing in papers. Specifically, if you don't have catch data or discrete integers, you're moving into that world of logistic regression or linear regression. Now, if you do have catch data, you're kind of going to move into this realm of more complex analyses. They have all the same underlying assumptions and theory, but that's going to be a negative binomial, or in the case of most of our data, we have a lot of zeros. And so that's going to be this special case called zero inflated models. And finally, for this little schematic here, you have the case of nonlinear models, which is referred to as generalized additive modeling. So this is an example of just a conceptual model that I came up with to go over the types of analyses I've started with over the last 15 years. And this kind of gives you an idea of what you could be doing. Another useful tool, though, that we're going to be talking about each one of today's talks is how do you actually do it? Now, I'm going to walk you through my conceptual model of how to build a model, how to perform a statistical analysis. And I want to note that because these are only 15-minute talks, we don't have time to go through each step in every talk, but everybody will be touching on different aspects of this. And I encourage you to think about this conceptual model as you're listening to talks today, and especially as you're reading the handouts. So the first thing I've always encouraged everyone to do, and I always do because I'm excited when I get data, is to just plot it. And when you plot your data, you should be considering factors that may cause you warning or maybe reason for you to think about a different approach. That includes outliers, data that are far outside the data space, collinearity, and that's when you have two of your X variables that are highly related. That can cause your model to produce unusual results at times. Zero inflation, again, that's very common in catch data where a lot of our samples don't catch that species of concern or that item of interest. Incomplete data, where do you have NAs in your data set? And then something that we all need to consider when we're using monitoring data is that temporal or spatial relationships in our sampling design. Now, once you look at your data and you walk through the previous conceptual model, that kind of key of where you should start with your analysis, go ahead and throw a model at your data or your data at a model. Now, this is going to be an iterative process because I promise you, if there's one thing that I can guarantee about everyone's analysis, the first model you build will not be the final model you present. That's just not the way modeling works. That's not the way statistics work. So choose a model based on your best knowledge and then evaluate those results and see, is the type of statistic you're using or the variables you're including or the transformations of those variables, is that the best approach? Things to consider here that are quite important are whether or not you're taking an information theoretics or a hypothesis testing approach. Now, this is a really important key, so I do want to touch on it just a little bit. Hypothesis testing is pretty simple to understand. It's you go into your project saying, I think Y is driven by or associated with this variable and this variable. And so those are the only two variables you collect data on. Those are the only two variables you have in your model. Information theoretics is going to be really powerful if you're leveraging IEP's data set. And information theoretics is where you just throw the kitchen sink at the model and you let the model tell you which variables are important. So this is just one example of the kind of things you need to be thinking about as you're going through your first round of this iterative process in modeling. Now, unfortunately, this kind of gets complex and it turns into a bit of a figure eight, because as you think you have the right model, then you kind of move into this second phase, which is model validation and model improvement. So that's kind of when you know the variables you have, you know the statistics you're running. At this point, you want to dig deep and think about the assumptions of your model. You want to compare your model predictions to the data. Think about influential observations. Think about whether you're meeting those assumptions of independence among your data, variance, homogeneity, that your residuals, when you plot it across your X variable, you don't see these crazy patterns or a hump in your residuals, and that a histogram of those residuals look normal. And then once you've kind of ran through this figure 8 until you don't think there's any way to improve your model, now's when you think about how do you visualize, how do you interpret your model results, and how do you present those to your friends and colleagues. And at that point, you either continue back in this figure 8 process or you work on your model presentation. Now, speaking of this process and how each one of our speakers are going to show us different aspects, the first talk today, the first actual training, what we're calling micro training, is going to be led by Pien, and that's after me. That starts at 8:50, and that's going to be looking at different ways to explore your data. Following that, we have Emily Ryznar, who is going to be giving us a talk on this categorical grouping and when you have categorical predictors. Talk 4 is going to be led by Trinh, where he's going to introduce you to this incredibly powerful classification approach. After that, to give you proof that this conceptual model in the background here isn't exhaustive, we've got Tim, who's going to be stepping out of this framework and teaching us ordination, which is a type of multivariate statistic. Multivariate is when your Y variable is a lot of variables, like a species community. We're then going to have a break. We're going to return to the second round of micro training, where Braden's going to start by introducing us to linear regression. Afterwards, Tyler's going to move on to what I think is a bit of an underused method of logistic regression. After that, anybody that uses IEP data, which I'm assuming is most of us, definitely wants to stick around for a pair of talks by Rosie, where she's going to introduce us to what to do when you're analyzing catch data, especially if those data have a lot of zeros in them. Her first talk will be on negative binomial, and her second will be on zero inflated negative binomial data. I'm then going to come back and give you a crash course in nonlinear modeling for the last talk of the second session. After lunch, you're going to have to put up with me a little bit more, where I'm going to give you back-to-back talks about mixed effects regression, which I believe is a modeling method that everybody should be using when they're using monitoring data, most likely. And then our last session, the advanced analyses, is going to finish off with Sam introducing us to regression in a Bayesian framework. Now, even if you don't think you ever want to do Bayesian statistics, this is going to be an invaluable talk to listen to, just so you can learn a little bit about the underlying theory and the language people use. After that, we're going to have open Q&A. And again, that's going to be at 2 p.m. today. I encourage you to bring data, bring questions, bring problems. So overall, today, I hope that we can provide you all with a suite of useful tools to kind of take away the fear that comes with modeling. Here's the list of sessions, and the website here at the bottom is where all those materials can be found. Now, I'm going to try to change screens very, very quickly. Let me know, please, if you cannot now see a website. Here's the website of where all that information is housed. We have all the talks with some recorded presentations. Each session has its own folder. For example, we can go to regression in R. We can go to the nonlinear modeling, and we have code, a data set, and a handout, which hopefully will load, where you can see here, and each handout includes information like background, and you can download by clicking the button here. With that, I thank you all for your time, and I think if there's no Q&A, which doesn't look like there is, I think we're almost ready to move to the next talk.
Great, thanks, Jereme.
Great, thank you, Christine.
And while we're getting those slides open, I just want to remind people that the training materials that Jereme just shared on GitHub, that link is available on our website.
Okay, now the first talk today, I'm excited and grateful to introduce Pien, who earned her MS in Marine Science at Moss Landing. And she's, and she's gonna walk us through the introduction to data exploration.
Hi everyone, my name is Pien. I work for DWR, and today I'm going to kick you off with a training on data exploration. So data exploration often occurs at multiple stages of an analysis. The initial data exploration is really important for finding the issues with your data and for getting an idea of what analyses you can perform. This training is going to include some examples of plots and code to help you look at relationships between variables, such as data over time, space, variability of your data, collinearity, distribution of data, how balanced your data are, missing data, and outliers. And so these are a lot of the things you can look at the beginning, but of course data exploration is going to continue as you conduct your analyses, as you develop more questions after your analyses, and so forth. I'm going to be conducting the majority of my data exploration using the tidyverse, which is kind of a grammatical language that is a separate package from base R, but you can conduct your data exploration using base R or other packages as well. So first step, prepare your data. I'm going to run through the next couple sections a little bit quickly so that we can spend more time on the plots, but there is a lot of prep that you'll need to do to get your data in a place to even get ready to explore. This I have seen in some of the groups we're in taking a really long time, and just be patient and really take a good look at what you have and what you need. So you want to load all the packages that you need, get your data. In this example, we're going to be using some data that I'm more familiar with from the Yellow Bypass Fish Monitoring Program. We are just filtering out the beach seine data from this fish data set, and we'll be looking at both the water quality aspect and the fish aspect of this data. I did save a copy for the training, but you can download the data directly from EDI. So one thing you'll want to do is develop your questions before you start your data exploration. You, of course, can continue to develop questions as you explore, but it can help you filter down what you want to look at if you have some questions in mind. So you want to think about what your response variables and what your predictor variables should be. And then you want to explore to make sure the data are set up correctly and that the parameters that you need are in the data set. So if your question is native fish abundance correlated with space, time, and water quality, for example, you'll want to make sure to have the appropriate time, space, and abundance metrics. So, for example, for space, you might want latitude, longitude, or you might want region, depending on your analysis. For time, maybe you want water year or month instead of just the date. So take a look at how R is seeing your data, the variables that are included in the data set, what class they are. So if they're in the wrong class, you won't be able to analyze the data the way you want. So just take a look there, take a look at the metadata to understand the data. And then make sure you have the relevant variables. For example, you'll need to calculate daily CPUE in this case from count and volume, and extract water year from the date, month from the date as well. And just a note, you will see me use this pipe fairly often. That basically connects a lot of different operations together. You can read more about that. It's part of the dplyr package. So I did some manipulation just to get down to 1 CPUE per day instead of how it currently is set up, and added zeros for species that weren't counted or weren't in the samples, filtered down to station, native species. So that's all here. You can take a look at the code. And now let's jump into looking at your data over time. So I'll skip this dot chart, but this is an option in BASAR for looking at your data by row. The very similar plot, though, is the point plot. Show the code here. So here we're looking at, this is usually a plot I make right at the beginning, just look at the data over time. Here we've got time on the bottom, date, some CPUE, and you can just see if there's any crazy outliers and get an idea of what the trends look like. So data over space, if you have a lot of stations, it can be good to check your latitudes and longitudes to make sure they're correct. Make sure there's not something on the other side of the world. You might also look at this to help you figure out how to divide up your regions if you want to split your analysis into regions. You might also be looking at spatial trends. So the first thing I usually do is use the leaflet package to look at my stations. I like this because I can kind of zoom in and out on the station. Sometimes it can be hard when you plot everything over each other. You can also decide what shows up when you hover over it. So for example, here we're showing the station name and the sum CPUE value. So really useful for exploration. And of course, you can also look at your data, like in this instance, you'll see that certain stations were sampled in 2013, but not the other years. So maybe you decide to exclude these stations, or maybe you figure out more why that is. Okay, so moving on to box plots. These are really useful for looking at continuous categorical relationships. So say your water quality responses are continuous and you're looking at it by station, which is categorical. Great way both to spot outliers and to look at the spread of your data. You can start looking at some of the patterns too. Conductivity is lower in BL4, for example. And you can look, I usually do box plots by multiple different parameters. So that was station. You might look at water year, or station and water year, which looks a little crazy here, but you can change the settings. And all these different settings all these different views will show different outliers based on how you've grouped your data. So helpful to take a look at that. Moving to collinearity. So scatter plots are really useful for looking at relationships between continuous variables. You can find outliers, you can see relationships that are interesting to explore, and you can see what is too correlated to include in your models. So for example, here water temperature and DO are pretty correlated, but you might see some weirdness going on here. You'll see it further if you separate it by station. Those could be outliers. Pair plots are really useful for figuring out collinearity because you can plot all of your variables together and just see the correlation values on those. So Secchi turbidity 0.63 is pretty high. You might consider removing one of those. Your distribution, probably have heard of a histogram before. So we can use histograms to look at the distribution of data and also find outliers. So some distributions that might be important to know for using in a model or determining your priors for a model. just put a couple different kinds here. Depending on your distribution, you're going to probably run a different kind of model, or maybe you need to transform your data. So this is something I often see when I plot my data, because I work a lot with count data, is a whole lot of zeros. This is called zero inflated data, and you'll learn how to deal with that later. If here we're looking at native fish, but if you look at all fish, it's a little better, but still really heavily skewed with lots of zeros and fewer coming out over here. Sometimes this will show you a weird outlier to the right or something as well, but plotting the distribution is really important first step for prepping for your modeling. You can do multiple variables using, this was a freak poly. I'm not sure what exactly it's called, but looking at I think this is a frequency plot of some sort, where you can look at multiple histograms basically at a time. And then, so if your data need to be transformed, you can use a histogram to look at the comparison between transformed and untransformed data. For example, here, turbidity, if we transform it, is normally distributed, and you can then continue with parametric analyses. Okay, moving on to how balanced your data are. So often you want to have balanced design for analysis, so you can just use the simple count function and look at your sample size by whatever you're interested in, station or year. You could also look at this with a plot, size your points by your sample size, and just take a look at how even those are. Missing data can be really important to deal with. So I like to use tile plots you can look at patterns this way. In some cases, it's a really nice way to look at your data, but it also highlights where you're missing data, which is probably cause for exploration. Maybe you fill these in, maybe you don't. But this is what I usually use for an initial glance at sample sizes and missing data. Okay, so moving on to outliers, you could definitely spend a whole lesson on QA/QC and outlier detection. We do have an entire working group dedicated at DWR to just providing outlier detection recommendations, and that's a lot. So I'm just providing a couple simple outlier tests here. I usually start with just looking at the data and visually identify outliers to flag. I like to use Plotly, which you saw a leaflet earlier. Plotly is an interactive way to look at your data as well. So if you go down here and run Plotly, well, let's just do it in here. You can hover over your data and see information like the value, the station code, and I like to code an index in. You see 2006 to help me identify outliers if I think something is an outlier. It gives me an easy way to filter that out or call it an outlier. So here's a screenshot of that. And besides that, you can use some actual outlier tests like the Tukey test or median absolute deviation. Here's an example of how Tukey outliers are calculated. These are what you see in a box plot, and it's based on the percentiles of the data. I've included some calculations that you can do, but you can use the Tukey test or the MAD test using a package from DWR. And I've just demonstrated that this is kind of what it looks like when you run the code. Tells you each set of data, is it an outlier or not? Is it an extreme, mild outlier? You can plot that and look at it to see if you agree with the determination. So once you find an outlier, you can either flag it and leave the data as is. And if you're analyzing the data, you might want to remove the outliers by replacing with NA, or replace the outliers with a mean, data from another source, or other methods. And once you've dealt with your outliers and explored your data, then go ahead and have fun with analysis. And that's it for today. Here's some references. Thank you.
All right, well, thank you very much, Kat. There are, oh, if you have questions, we have about 3 minutes for questions. Kat, I'll go ahead and ask you the first question that we have here. And this is by Pete Nelson, who's wondering, where do you get the package ODWG tools?
Yeah, hi Pete. So I can put the link in the chat. I think everyone has access to the chat, or have it sent out, but it's on, I think it was Michael Kuhofkin from DWR when he worked there that developed it. So it's on GitHub. I think Dave Bosworth might be maintaining it perhaps, but yeah, there are some tools being developed there, and I can share the link to GitHub page.
Yeah, that's an important thing to note for folks that are maybe a little bit newer to R, is because R is open source, it's very, very powerful. And there's literally 10 to 1,000 ways to do any particular thing you want to do. And again, because it's open source, people like you and me can actually create a package, host it outside of R, and you just have to find it, and you can upload it in R and use that package. I don't see any hands raised. Oh, there is one. Oh, where'd they go? Somebody, I think I saw his name, Teague, had a question. I lost you. Teague, I think I just gave you permission to talk if you have a question. You're still on mute.
Jereme, what's the name you're trying to give permission to talk?
Teague, T-E-A-G-U-E.
Yeah, there's a Q&A, says no, sorry.
Oh, okay. Wonderful. All right. Well, with that, if you do have questions that come up, remember, we're going to have that open Q&A at the end where we'll have plenty of time. We have another minute or so, so I'm going to hold off on starting the next talk just to make sure we stay exactly on time. Tim did have a comment, not a question, just a comment. I've been using R for many years now, and I still get very excited when someone introduces me to a new package that will make a world of difference in my work. Thanks. So that one's to you, Kat. And just a note about today's speakers, everyone's doing this volunteer. So please remember to thank them when you see them in virtual worlds or real worlds. And as per usual, thanks for joining us. Christine, can we get you to queue up the next talk?
Sure.
The next speaker is going to be Emily Ryznar, who earned her PhD from UCLA. And she's going to be introducing us to the challenge of what to do when you have a lot of categorical predictors.
Hi, everyone, and thanks for joining. My name is Emily Ryznar, and I'm a former California Sea Grant State Fellow with the Delta Science Program. Today, I'll be providing an overview of ANOVA, or Analysis of Variance, Kruskal-Wallis, and Multiple Comparisons Analyses. Let's get started. So let's quickly go over each analysis, starting with their similarities. Both analyses require a numeric response, think length, weight, etc., and a categorical predictor variable, often called a factor in these types of analyses, with more than 2 groups or categories per predictor. Further, both analyses require that observations are independent of one another. Finally, both analyses evaluate whether there are differences among groups. And ANOVA is basically a special type of linear regression without a continuous term, and more on this in the guidance document. It evaluates whether group means are different, accounting for variance around those means. Further, an ANOVA is parametric, meaning it assumes that model residuals or error terms are normally distributed and exhibit equal variance among groups. Finally, an F statistic is calculated to assess whether the null hypothesis, or if group means are equal, can be rejected. On the other hand, while Kruskal-Wallis is considered a non-parametric equivalent to an ANOVA, there are differences. A Kruskal-Wallis analysis functions on data value ranks instead of the values themselves and does not produce model coefficients like an ANOVA. Further, a Kruskal-Wallis evaluates whether group medians are different following ranking. A Kruskal-Wallis is non-parametric, but does assume that response values follow a similar distribution among groups. Finally, an H statistic is calculated instead of the F statistic to perform hypothesis testing. So what are multiple comparisons? Multiple comparisons, sometimes referred to as post hoc analyses, are methods to explore pairwise differences between groups following a significant main result that may tell you that there are differences among groups, but not necessarily where which groups are different. When running multiple comparisons, one should control for increasing experiment-wise type 1 error rates by adjusting your level of significance to be more stringent. And there are various methods for doing so, including Tukey, Bonferroni, and Benjamin E. Hochberg, but more on this in the guidance document. So let's apply these analyses. In a hypothetical scenario, let's say that there is a disease outbreak in the early 2000s that stunts the growth of older cell-modded life history stages, leading to similar sizes across all stages. However, it is unknown whether this disease specifically impacted Chinook salmon migrating through the San Francisco estuary. So by collecting a bunch of data, in our case, we'll be using IEP's Liberty Island beach seine data, and by choosing a year in the early 2000s, in our case 2004, we can utilize an ANOVA or Kruskal-Wallis to evaluate the question, are fork lengths similar among Chinook salmon life history stages in 2004? Or in other words, is the disease present? So now I will transition to R to first run through exploring the data and then go over model application, evaluation, and interpretation. And I will return to the PowerPoint for final model presentation. So let's go to the code. Okay, so we have our data and we have our question. And before we go about analyzing that data, we need to first import it and prepare it for analysis. So our data file is this li_sane.csv file, and we can go about importing that here. And then in the next few lines of code, I go about subsetting the data to only include observations from 2004, only including observations for Chinook salmon, and then only including life history stages 2 through 5 in order to help address our question. And I also include more informative labels for those stages. However, for the sake of time, I'm going to just quickly run these lines of code here, and we're going to basically start with this new subsetted data frame, CH2004. So taking a look at this data frame, you can see there's multiple variables within it. But for the purposes of our analysis, we're only going to be focusing on this fork length variable here, which is our response variable, and then our predictor variable here, stage. So we can further take a look at this data by plotting the raw data here. And so you can see here again that we have our predictor variable on the x-axis with 4 different groups or life history stages: fry, par, silvery par, and smolt. And then our response variable on the y-axis, and then multiple measurements or observations of that response variable per group. And so our ANOVA or Kruskal-Wallis is going to assess whether there are differences in the fork lengths among those groups. So ideally, before beginning our analysis, we would check for and remove outliers, but because we don't have the raw data sheets, we can't really justify removing any of those. So we're going to bypass the outlier step. However, we can check to see if there's any missing values in our response variable. Running this line of code here gives us a false output indicating that there aren't any missing values in our data. Okay, so we are ready to run our first analysis, which will start off with our one factor ANOVA. In this case, our one factor is our predictor variable stage. We have one predictor variable and therefore one factor. Okay, so before we begin, we need to make sure that our predictor variable stage is recognized as a factor or a categorical variable by R by running this line of code here. So that works. Otherwise, we wouldn't be able to run our ANOVA. Okay, so now in order to run our ANOVA, we'll be using the LM function, this linear model function. And you can see that the syntax follows a similar syntax as other linear models you may see in this micro-training session, where you have your response variable fork length by your predictor variable stage, and then the data frame that those variables are coming from, in our case, CH 2004. You can also see that I have two different ANOVAs run here. The first run is run on untransformed fork length data. The second one is run on reciprocally transformed or 1/x transformed fork length data. And so transformations basically help your data meet assumptions for parametric statistics, meaning normality assumptions and that equivalency of variance assumptions among groups. And various transformations can be utilized. We use a reciprocal transformation, but square root transformation, log transformation can also be used. And if your data still doesn't meet parametric assumptions following transformation, then a non-parametric equivalent such as a Kruskal-Wallis should be utilized. So I ran two different tests because in the next stage or the next step, we're going to be checking for those parametric assumptions. So let's run both of these models here. Okay, in the next step, we're going to be visually inspecting fitted model residuals for that normality assumption and then the equal variance assumption. And histograms are useful to inspect for that normality assumption, and box plots are useful for checking for that variance assumption among groups. So let's plot some histograms and box plots for both of those models' residuals. You can pull out the model residuals here by just doing this $ residuals to pull out the residuals. Okay, so you can see in these plots on the right, in the top row, we have residuals pulled from a model run on untransformed fork length data. And the bottom row is our residuals pulled from a model run on transformed, reciprocally transformed fork length data. So you can see that for normality, both the untransformed residuals and the transformed residuals generally follow that characteristic bell-shaped curve that is indicative of a normal distribution. So these are both probably okay. For variance, you want to check to make sure that the length of these box plots or the variance is equal among groups. So you can see with the untransformed residuals, the variance in the length is pretty unequal among groups. This likely is not okay. However, with our transformed residuals, you can see that the box plot lengths are relatively similar among groups. So based on this visual inspection, we can conclude that a model that was run, an ANOVA model that was run on reciprocally transformed fork length data is likely the most valid, and we can proceed with assessing that model output or interpreting that model output. Okay, so these next few lines of code here are basically ways to statistically test whether your model residuals meet normality and variance assumptions. But for the sake of time, I'm going to bypass those lines of code, but please see the guidance document for more information on this. Okay, so let's proceed with viewing a summary of our model run on transformed data. So for our ANOVA output from the linear model function, you can see that it outputs a bunch of useful information, including our coefficients and their estimates, whether those coefficients are significant or not. And please see the guidance document for more information on what this model output means. It also outputs the residual standard error, your R-squared values, and most importantly for reporting our final model, we want to pay attention to this F statistic here, 336.1, our between group degrees of freedom 3, within group degrees of freedom 304, and then our significant p-value here, which indicates that there are significant differences in fork lengths among Chinook salmon life history stages in 2004. However, if we really wanted to really wanted to see which stages were different from each other in fork length, we could run a multiple comparisons test. And we'll be using this GLHT function here, which stands for General Linear Hypothesis Testing function. And this function is found in the package multicomp. So let's load this package here. And then the syntax for this function is basically specifying what ANOVA model or what model we want to utilize. And here we want to utilize our ANOVA model run on that transform data. We want to specify that it's a multiple comparisons test using this MCP function here. We want to specify what we want to compare between. In our case, we want to compare between stages. And we want to specify what method we want to utilize for that multiple comparisons. And the Tukey honest significance difference test is a common multiple comparisons test run after an ANOVA. So let's run this line of code here and then view a summary of that. And so here you can see we have our multiple linear hypotheses or multiple comparisons. And we can see in the p-value column here that all of them are significant, meaning that all stages were significantly different in their fork lengths in 2004. We can further visualize these pairwise differences by creating a compact letter display. And you can see in this output that no stage shares a letter, further indicating that all stages were significantly different from each other. Okay, so what happens if we weren't able to ultimately transform our data to meet parametric assumptions? We can use a Kruskal-Wallis to analyze the same question. But before we do so, we need to first check that assumption that fork length distributions follow a similar distribution among groups, among stages. And we can do so again by plotting histograms of that fork length data among the different groups. So we can run these histograms here. And you can see that among the different groups, among the different stages, fork length roughly follows a similar distribution. However, fork length for pars seems to be pushing it a little bit. However, for the sake of simplicity and time, let's assume that they all are perfectly follow a similar distribution and proceed with the analysis. Okay, so to run a Kruskal-Wallis analysis, we'll be using this Kruskal.test function, and this is in the package FSA. So we can load the FSA package, and you can see that this Kruskal test function follows the same syntax as our linear model function that we ran for our ANOVA earlier. So let's run this Kruskal test here and then view the results of that. And you can see that the model output for the Kruskal-Wallis test is much more simple than the ANOVA output from before. Here we just have our Kruskal-Wallis H statistic or chi-squared value 231.52, our between group degrees of freedom 3, and our significant p-value, again indicating that there are significant differences in Chinook salmon fork lengths in 2004, or no hypothetical disease. We can further assess pairwise differences by running a multiple comparisons test. And a common one for a Kruskal-Wallis is a Wilcoxon test. And we'll be using this pairwise Wilcox test in the stats package to do so. So let's load the stats package. And the syntax for this pairwise Wilcox test function is specifying the response variable directly from the data frame itself, not from the model that we created. And then the predictor variable stage, and then what method we want to utilize to adjust for those p-values to control for those type 1 error rates. In this case, we specified we want to use the BH or Benjamini and Hochberg method, but there are multiple options for this. So let's run this line of code here. And again, you can see that all pairwise comparisons are significantly different from each other, again indicating that all stages had significantly different fork lengths from one another in 2004, so no disease. Okay, so to present our one-factor ANOVA findings, we will need to report our F statistic value, the between and within group degrees of freedom, and our p-value. So in text, we can say fork length was significantly different among Chinook salmon life history stages in 2004, with our test ANOVA, our between and within group degrees of freedom, our F statistic, and our significant p-value, followed by saying, and multiple comparisons revealed significant differences among all stages. We can further present our results graphically, and box plots are useful to visualize and compare variance among groups as represented in the graph on the right. Adding the mean fork length, the blue points for each stage, illustrates even more information. If the mean value for one stage falls outside the interquartile range or shaded box region of another stage, it's assumed that those groups are significantly different. As we can see in our figure, none of the means blue points for each stage overlap with the interquartile range of other stages, meaning they're all significantly different. And this is what we found with our ANOVA and multiple comparisons. And if applicable, you can add your multiple comparisons letters to further help your reader visualize differences. For our Kruskal-Wallis, we can textually and graphically present it the same way, though we will need to report our H statistic, 231.52, our between group degrees of freedom, and our significant p-value. And then also in our graph, we need to report that our post hoc letters, our multiple comparison letters, are from a Wilcoxon post hoc test instead of our Tukey post hoc test in the figure caption. All right, thank you for listening. I'm happy to take any questions.
Wow, thank you, Emily. That was a beautiful job walking through the figure 8 of how to do an analysis. If you have any specific questions, feel free to raise your hand or ask them in the chat. For now, there was a number of quick general questions that I want to run through. Barb wondered whether we should download any materials ASAP or will they stay up? Those are going to stay live until we do this again. Again, I'm going to send out a survey to see whether this works for folks. And if people like it, those materials are just going to stay until somebody updates the lecture. Teak is concerned about the quality due to the sharing online and bandwidth. I think a good way to view these talks is similar to when you're doing something new. An example comes to mind is when I was putting in some irrigation this summer for my backyard, for my dogs had somewhere to lay around in the grass. And it had been years since I put in some valves of PVC pipe. And so I went ahead and watched a Google video, went outside, looked around, messed around, and then came back and watched the video again. So I think you should just view this as a first crack at understanding these analyses. Elaine went ahead and entered the link to the ODWG tools package. And then Haley claims she has a stupid question, but I do not believe that any questions are stupid. So if you go to our website and you want to download any packages, here's an example of Emily's same data. If you click on the link and then move over to this little button that says download, that should get you what you need. So if that doesn't work for you, shoot another message in the chat and we can try to figure it out a little bit later. Well, so this is a big question from Keith for Emily. We've got a couple minutes, so I'm gonna go ahead and try to do it. The e-mean package authors advise against compact letter displays. The e-means package recommends against using the multiple letters. Yes. So the question is for Emily, do you agree? And can you offer any comments on how to best communicate the differences between groups? This is a technical question. So Emily, if you can answer that, otherwise I have thoughts.
Yeah, Jereme, you might have to answer this one because I personally have never had any problems reporting compact letter displays in any issues with that. But if I guess if not, then maybe plotting like the box plots and seeing whether the links to those box plots overlap with the interquartile range of other box plots, maybe help visualize significant differences without using those compact letter displays. But I don't know, Jereme, if you have any other.
Yeah, so I think the core of this question has to do with, oh, am I muted? No. I think the core of this question has to do with the philosophy of p-values and distributions. So that's actually a much bigger question that I think would be good to circle back to after Sam's Bayesian talk. And I imagine Sam's going to touch on this a little bit. So for now, Keith, I would say put a pin in that. And I would encourage you to bring this up in the open Q&A at 2 p.m. And Haley says that does not work, but Kat is typing. So Haley, I will reach out to you. Haley, can you put your email address in the chat? And you and I can have a side conversation probably after this session, and we can even video link to make sure that you can do that. And then one last question before we move on. Yeah, Pete notes that regarding video quality, you can follow the talk, code, and figures pretty closely using the PDF file provided on GitHub. So that's another thing that you can use is the talks will generally follow the outline of the handout. So you can actually have that in a separate window if you're struggling. So with that, I think we need to move on. The next speaker is going to be Trinh from CDFW and IEP, who's going to be talking to us about classification trees. And Trinh earned his BS in biological sciences at UC Davis. Take it away, Trinh.
Hi everyone, so welcome. In this session, we'll be talking about classification trees. My name is Trinh Nguyen. I am an environmental scientist specialist working at CDFW and IEP. And I've had a lot of experience working with machine learning algorithms and specifically with tree-based approaches. And so hopefully I'll be able to give you guys a good primer on this topic today. As an outline of the presentation, I'll first touch on the general modeling framework that was provided with this micro workshop to basically outline the types of conditions in which you might want to use this model. From there, I will go on to define what a classification tree model is and talk about the intuition on how to grow it. After that, I'll jump into the application of this model in R using a case study as an example. I'll walk through the modeling, coding syntax, how to fit the model, how to evaluate the model fit, and how to present the result from your model. From there, I'll conclude with several minutes of answering questions if there are any for me to answer. So, the general modeling framework, we see that we are in the top right corner of this figure, and there are three conditions that need to be met in order for us to consider using this model. Those three conditions are: one, is our response variable categorical? If it is, then two, do we have predictors that are categorical? If we don't, then three, does our categorical response variable have more than two response categories? And so if all three conditions are met, then you can potentially use this approach on your data set. Now, this is a very specific use of the classification tree model. And in general, the classification tree model is a little bit more flexible in terms of different conditions that it can be applied to. But for the conditions that are on this flowchart, this is a perfectly fine use of the classification tree model. So what is a classification tree and what's the intuition behind growing it? So a classification tree is a specific variant of a more general model called a decision tree model, in which the response variable is categorical. So when I say categorical, this means that the values in that variable can only take on discrete and fixed possibilities, right? So for example, a column that contains the name of different animal species would be a categorical variable. As for the structure of the classification tree, it is very similar to a dichotomous key. And so if you used a dichotomous key before, you have used a classification tree structure before. For those of you who haven't, this is an example of a very simple dichotomous key in which various morphometrics are used to classify different classes of animals. And so how you would use this would be you would have an unknown sample and you would compare the characteristics of your unknown sample to what is laid out on this key here to arrive at a decision point. So the first thing you would look at in your unknown sample is to say, does my sample have fur or not? And if it does, then you're done. Your unknown sample is a mammal. If it's not, then you continue on in the decision tree or the dichotomous key until an outcome is reached. And so in this case, you can see that this is a classification tree in which the response variable are the various classes of animals, and the predictors are the various morphometrics of these classes of animals. You can also see from this dichotomous key the intuition behind how to grow this tree, because at the very top of the key, you have your entire data set, and that entire data set contains different mixtures of all of your response classes. And so in order to grow the tree, all you do is you split that data set into smaller, more homogeneous groups that better define your response classes. And so it's a very simple directive that you give to the algorithm, but if you iterate that directive over and over and over again, you can split the data set into groups that are more alike with itself than with each other. And at that point, you can determine when do you want to stop the model and describe your data set. Okay. And so now moving on to the application of this model in R, I will be using the CHIPS Island dataset as a case study dataset. This is a dataset maintained by the U.S. Fish and Wildlife Service. The study question that I'm interested in will be, what are the environmental conditions associated with various levels of longfin smelt catch in the CHIPS Island trawl? And I'll be using two main packages to help me through this process. So a little bit of background on the CHIPS Island trawl itself. It is a mid-water trawl that samples at CHIPS Island. I'm using data from 2011 to 2021, and that's just an arbitrary choice. The trawl itself has a very high sampling rate that has caught longfin smelt in every single year of the data set. The response variable, in order to satisfy the conditions that were laid out in the framework earlier, I changed the continuous catch variable into a 3-class classification variable, in which the first class is no catch, the second class is low catch, which is when the daily catch of longfin smelt is equal to 1. And then the third class is high catch, when the daily catch of longfin smelt is greater than 1. To then match the response variable, I am using 6 environmental predictors whose data were collected during the sampling event itself. And so the study question again is, what are the environmental conditions associated with various levels of longfin smelt catch in the CHIPS Island trawl dataset? For the two packages, the R-part package is the actual decision tree package itself and contains the algorithm itself. The caret package is an optional modeling workflow package that I personally like to use because it provides all the tools that you will need as a modeler to go from the beginning of the model to the end of the model. And so the first step in the modeling process is to split the data set. And so here I'm using a 75 and 25% data split, which means that 75% of the data is used as training data and 25% of the data is held back and used as testing data. And so it's essential to do this step and to split your data set, because for these machine learning algorithms, they can very easily overfit the training data set. And just because your data performs really well on the training data, that doesn't mean that it can generalize well over new data that you collect. And so that is the purpose of the testing data set. In order to do this, I like to personally use the create data partition function from the caret package, which returns an index of rows, a row index that you can then use to split the data set. This function takes in 3 different arguments. The first being y, which is your response variable, p, which is the proportion of data set you want to use, and list, which is should it be returned as a list or a vector. After splitting the data, you can then train the model. And the training process is composed of 2 separate processes itself. And both these processes are encompassed in a workhorse function called the train function of the caret data set. And so obviously there's a lot of arguments here, and so I'm just going to push through them because of time. So please refer to the handout if you want additional details. But starting from the top to bottom, the first thing you have to specify is the model formula. The second is what data set do you want. The third is what algorithm do you want. Here we want R-part. And a action is a specific argument for R-part, and it tells the algorithm how to deal with missing data. Parms is an argument, again, that is specific to R-part, and it determines the splitting criterion for the algorithm to use to grow the tree. And so these first 5 arguments determine how the model is trained. The next 3 arguments determines how the model is tuned, right? And so the tuning process here is important for machine learning because there are tuning parameters that determines how the algorithm fits the data set itself. And so if you try different values of tuning parameters, the model will fit differently. And so it's important to do this in a cross-validation framework because for machine learning algorithms, they are entirely driven by the data set. And so there's not really an accepted value of these tuning parameters to use in order to get the best fit of your data set. And so by using cross-validation and trying different values of the tuning parameter, you can get an approximation of what value actually works best for your specific data set. And so TR control controls various aspects of the cross-validation approach itself. Tune length controls how many values to try for your tuning parameter. And then metric controls the evaluation metrics that will determine how well your model is fit. Okay. So after you train the model, you can then evaluate the tuning process to see if the parameters that you have chosen does a good job at approximating the value that you should be using to describe your data set. And so this is facilitated by the plot or the ggplot function on the caret package training object itself. And so when you use these 2 functions, either of these functions on the training object, it will spit back at you a visualization in which the y-axis is your evaluation metric, and on the x-axis is your tunable parameter. And so for our part, there's only one tunable parameter, and that's something called a complexity parameter, which determines how big of a tree to build. And what you're essentially looking for here is either a maximum or a minimum in the curve across all the values that you tried. And so because we are using kappa, we want to see a maximum in the curve. And luckily for us, we see that 10 values we tried for both models does produce this maximum in the curve. After the tuning process, you can then evaluate how well your model is fitting. And there are 2 ways to do this. The first is to calculate your evaluation metric itself on the training data set and the testing data set. And that's what I've done here, is to calculate kappa on the training and testing data set for both of our variants. We see that the entropy variant performs better than the Gini variant in both the testing and training data set. But overall, kappa is pretty low because kappa ranges from 0 to 1, with the value of 1 being a perfect fit. And so we will have to dive a little bit deeper into why this is the case. And so that is the second way to evaluate model fit for a classification model, and that is to use something called a confusion matrix. And the confusion matrix basically lays out your predicted versus observed across all of your response classes. And so to facilitate this, you can use the confusion matrix function in the caret package. And this function takes in 2 forms of arguments. So the first form is that it will take in the trained object itself. And so if you do it this way, it will provide you a confusion matrix of the training data set. The other way is to provide it with 2 vectors. The first vector being the predicted values from your model, and the second vector being the observed value from your data set that you just predicted on. And so this is generally done for the testing data set. So for us, in this case study, we see that the reason why kappa is so low is because even though the model does a really good job at classifying the no catch class, it does a really poor job in classifying the high catch class and a very, very poor job in classifying the low catch class. So for the high catch class, it only gets it right about 50% of the time. And then for the low catch class, it almost never gets it right at all. And in the testing data, you see that it never predicts a low catch prediction, even though there are low catch events in the testing data set. And so because 2 of our 3 classes, the model fit very poorly to, the kappa value is extremely low. So let's say that I was happy with my fit of the model. I can then go on to visualize the results from the model. And there are 2 ways to do this. The first is to just visualize the tree itself. And you can do this from the rpart package, but that produces a fairly lean visualization. And so this specific visualization is created using the rpart plot function from the rpart plot package. The other way to visualize your data set is to provide and to visualize the variable importance of your model. And so this is done using the combination of 2 functions. One is the var imp function from the caret package that is used on the train caret object. And the other is the plot function, or the ggplot function of the var imp object that you have just created. And so that will return to you these graphs here. And essentially, variable importance in a classification tree measures how many times that variable was used by the model to describe the data in the data set. And so if a predictor is higher up in the decision tree, or is used more often in the decision tree, it will rank higher than another variable that is lower in the decision tree or used less often in the decision tree. And so for our specific case study, we see that the most important variable in determining Laughlin's felt catch at the chip's island trawl is water temperature. After that, it is the water clarity in the area and the rest of the environmental conditions. And so that is essentially the presentation. We first talked about the general modeling framework, the type of conditions you might want to use this model in, then moved on to defining what a classification tree model is and the intuition of the approach, then talked about how to apply this in R. And now I can take any questions that people would have on this presentation. So thank you.
Thanks, Trinh. That was a great crash course in machine learning. Again, machine learning is one of those tough topics, so I encourage you to walk through the handout. If you have any questions or comments, we have time for 1 or 2. I do want to address one of the comments that was in the chat, and that is, Flora, any chance you could reset Wi-Fi? Concerns about the quality. So the quality, I could read all the text even on Emily's talk. It is, small and tiny bit blurry, but I could still make it out. I would recommend you turn off a VPN and close any windows you're not using, and any devices in your house that are linked to the Wi-Fi. I would maybe turn off their Wi-Fi. Those would be my recommendations to make sure that we have everyone get the best video quality possible. I'm not seeing any hands. Oh, there is a new one. So Trinh, Janice Cook has a question. Does developing a classification tree require a machine learning approach? Sorry, I was confused, but by maybe a mix of the 2 topics.
Yeah, so in my mind, a classification tree model is a machine learning approach. It is a non-parametric approach, which depends entirely on the data, the underlying data. And so because of this learning directly from the data, in my mind, it is a machine learning approach.
Yeah, to add to that, a machine learning approach is the best way to do a classification tree, but you can do very simple rudimentary trees in a non-machine learning framework. And we can talk more about that in the Q&A. But for now, we do unfortunately have to move on to the next talk. Our final speaker for this session is Tim Malinich, and he's going to be introducing us to multivariate statistics, specifically ordination. And Tim earned his PhD at Purdue. Take it away, Tim.
Hello, everyone. If you've been hanging out in these statistics courses for a while now, hang in there. And if you're just joining us, welcome. My name is Tim Malinich. I'm an environmental scientist for California Department of Fish and Wildlife, and I'm going to be covering the introduction to multivariate statistics, specifically that branch which deals with ordination. So throughout the day, if you've been hanging out with us, we've been mostly covering univariate statistics. These are statistical analyses that look at usually one predictor or a couple predictors with one response. And I often like to look at these things with columns from a data set, for example. So I might have temperature as my response variable and regions as my independent variable. I have a couple different regions here, so maybe I would be doing a ANOVA to see if my different regions have different temperatures. But if I were thinking about the stations in the survey that I'm responsible for, the summer donut survey, I know that there's lots of different environmental variables that are important. And I want to look at a suite of environmental variables. So that's multiple response variables. So I'm going to need to do multivariate statistics here. So instead of looking at one response variable, I'm really looking at a matrix of variables. So in this case, as my example, I have temperature, water clarity from Secchi, and conductivity all up on my response side of the equation. And I continue to have my regions on the independent side. So here I'm looking at these different response variables, not individually, but collectively as a group as they change across these regions. The good news is that of all the univariate stats, there's usually an analogous multivariate stat that goes with it. So if you have continuous data, for instance, you're looking at environmental variables, there's something for that. Maybe you're interested in how communities change, so you have lots of absence and presence data, lots of zeros. There are some multivariate statistics that are better aimed for community. You might be thinking about diet data, stomach content. So I'm just doing the introduction to multivariate statistics. So there are a couple of commonly used ones that I don't really have time to get into, but you've probably seen the MANOVA or its permutational variant, the PERMANOVA. These are really great options if you're looking for just looking at a quick group of matrix of response variables and a couple of independent variables. But a much larger branch of multivariate statistics is on the ordination side. So the names that you might recognize from this are principal components analysis, which I'll refer to as PCA for a lot of this talk, the factor analysis, discriminant function analysis, another very common one called NMDS, or non-metric multidimensional scaling. If you want to know more about a lot of these different methods, I definitely recommend checking out a stats book like Numerical Ecology with R. There's lots of different editions, but the more recent edition will probably have the most up-to-date functions. You probably want to go with the, I believe it's a 2019 reference. But one thing I want to point out is if you're using the program R and you're going to use an R function to run a stat, if you go to the help page for those R packages or R functions, then always at the bottom of those explanations is a set of references that deal with that particular statistic, or sometimes they're books. So we're going to focus more on ordination today. And here we're going to be inputting many response variables. Now, the challenge of many response variables, and this is the challenge to multivariate statistics in general, is what we really want to do is try to take very complex data sets and make them easier to interpret. So you can imagine if you were plotting out your response variables, you could easily put in one variable on the x-axis, one variable on a y-axis. We do this all the time. Then you could color a variable. There's a third dimension. And maybe you could add a third 3D plot. Now you've got a fourth dimension. But now we're starting to get so complex that it's going to be very difficult for us to actually see any patterns if there are any. So the whole goal of multivariate statistics is to try to help us understand these complex patterns. So the output of a multivariate statistic often utilizes new dimensions and dimension reduction. taking the numerous response variables that we're inputting and condensing them, combining them into something that's easier for us to interpret. This could be a valuable tool later on if you're doing something like a regression analysis and can help you avoid overfitting by reducing the number of dimensions you have. And we'll talk about that a little bit more later. Ordination in general often starts with a visual interpretation, but there are quantitative ways to test that. So be prepared to strap in for lots of plotting if you're planning on using ordination. So a lot of what I'm going to talk about for the rest of this talk will be principal components analysis. This is a really great analysis to use with environmental data that uses continuous data sets. The reason for that is it relies on Euclidean distances to look at the positions of your different points from each other. And it'll take all your different response variables and produce many dimensions that explain decreasingly amounts of total variance from your total matrix. A little bit different from another common statistic, non-metric multidimensional scaling, which is often used for community data. This works out better with community data because it relies on linking in order to separate out your points. You can also use different types of distant measures with NMDS, so that could make it a little more flexible of a tool if you have a complex data set. You can actually set the number of dimensions when conducting an NMDS, and that comes with the caveat of the fewer dimensions that you have, the harder it is to combine all those variables and still hold in a bunch of the variance. The reason I want to start with principal components analysis is, as an introduction to ordination, it's probably the simplest of the different ordination analyses. And one of the reasons is that the variables that we're combining are combined in a linear fashion, so that you could easily look at how a variable's magnitude and direction influences the new dimensions you're making. So those new dimensions we call principal components. So each one of these principal components represents a portion of all the variation that was previously in that data set you put into it. Each of these principal components is considered a unitless axis. Each of those principal components, as I mentioned earlier, represents a proportion of variance. So if we're looking at this summary table on the right, we can see that our principal component 1 here is representing about 33% of the variance. Principal component 2 represents about 14% of the variance. And collectively, if we were to plot them together, they would represent about 47% of the total variance, at least at this one plot. Now, for our principal components analysis, you should have one component for every variable you have. But by the time you get down to your last principal component, you're representing very little of the variance. And those principal components could probably be dropped. And this is how we get to that dimension reduction, which was our goal from the start. Another useful component of principal components analysis is that each of our principal components are considered orthogonal to each other. So they're independent of one another, which is why we can do things like plot them out on an X and Y axis. They're not related to each other, so we can plot them in this manner. Ordination requires a lot of visual interpretation. It will require plotting lots of different principal components together to see how variation varies among your principal components, and see if, for instance, if you have different groups that you're interested in, seeing if those groups are clustering with that variation. And you could take those new principal components, now fewer because you could drop some of the lowest ones, and use them in further analyses such as a regression. So as an example, I want to use the Summertonet surveys data sets. We collect lots of different environmental variables, and a lot of times these environmental variables relate to one another. So it really makes them ideal for combining with their principal components analysis. So we're going to conduct a PCA and then use a visual interpretation of our regional groupings for the delta smelt life cycle model to see if the regions from that model are showing the differences in environmental variables that we see among our 40 stations. So on the right-hand side is a picture of our survey stations, and you could see the coloring of the delta smelt life cycle regions. We have the what is called the far west in this image, but later on I'm going to refer to it as the San Pablo stations. Then we have the west stations, which are essentially Suisun Bay and the Confluence. Our north stations, which is Sacramento and the Sacramento Deep Water Shipping Channel, and the southern stations, which cover most of the San Joaquin River. So in the base R stats package, there's actually two different principal components analyses. They're almost exactly the same. We'll be using the top one right here, the PR comp. And then if you're interested in NMDS, you need the vegan package, which has the meta DMS function, and two other ordination techniques that might be useful to you are correspondence analysis and redundancy analysis. Both of them are in the vegan package. So what happens when we run PCA? Well, R makes a lot of this very useful and simple. The PCA is going to take the data set that you're putting in, and it's going to calculate a covariance matrix. So it's going to identify the correlation among your variables, which I said earlier is really redundancy in that data set. And redundancy means that those variables can be combined and the extra information removed. So each principal component is made by essentially rotating the axis to move through as many points as possible and maximize the variance within the data set. If we look at a summary of this, what you would see is in order, the first principal component should have the most variation, second one, the second most variation, and on and on. We're actually looking at the code for running this. You'll see the PR comp function here at the top. This is our data sets. R will automatically center and scale your data set. You'll save that as an object, and that object will have your standard deviations, and this contains the information for your eigenvalues. Eigenvalues are essentially the calculation of variance that is contained in each principal component. The rotation is what I was just describing with the axis and how it's moved to maximize variance among all your points. The rotation is what we also call the eigenvectors, but we'll take another closer look at that. Center and scale are vectors that contain the values used to center and scale the data sets. And X here is a set of coordinates that is your data set now newly projected into these new principal components. So here we have our principal component 1 and 2 plotted out here. We can see that we're including the amount of variance that each one represents. And on the plot itself, I haven't put out my points yet, but what we could see are the eigenvectors. These are our original variables. The eigenvectors represent the magnitudes and directions those variables are going along each axis. So along principal component 1, as we move to the right, principal component 1 has values with higher microcystis ranking, higher Secchi readings, higher temperatures. And if you were to move to the left, they would have lower temperatures, lower microcystis, higher turbidity measured in NTUs, and higher conductivity. Again, move to the left on PC1. On PC2, we see as you move up, we have increasing severity of weather, and as you move down, we have increasing depths. It's important to look at multiple components to try to see how variance is being distributed by your data set. So here we have PC2 now on the x-axis, PC3 on the y-axis, and of course our vectors look completely different as a result. And we see with PC3, a lot of the changes are now with turbidity and temperature rising as you go up, depth and waves severity increasing as you go down. If we start putting our points onto this, we could see we have just a nice cluster of points, a lot of things in the center here. We see some points are really far out on our PCs. These outliers are something that we might want to revisit again in the future. We can use labeling to identify where these points come from. One thing that you can run into with ordination techniques is sometimes outliers in your data set will completely drive some of your components. In that case, you might consider dropping an outlier and rerunning your analysis. Even without coloring in these points, we kind of get an idea of how our stations from our data set are being distributed. I can even make some predictions with points moving towards higher salinity, higher turbidity, more increased severity in waves. These are probably going to be things closer to San Pablo Bay. Whereas over on the right-hand side, higher temperatures, higher microcystis. These are probably going to be in regions like the South Delta, where we typically see those. And once I color code that, that gets confirmed, not just because I know every slide ahead of time, of course. So as I said, here's our South Delta pulling aside here, and our San Pablo Bay stations are on the left and towards the top, being driven a lot by connectivity. We don't see a ton of separation in the center here, where we have West Delta and North Delta. So because I don't see a lot of separation there, I'm going to explore other principal components to see if I could drive apart all four of these regions. So here I have PC1 and PC5. In PC1, I have 37% of my variance, and in PC5, I have 9% of my variance. So in this case, I'm looking at other principal components, and that's coming at a cost for the total variation that's being explained by my plot here. So before I was explaining almost half of my variation, now I'm explaining less than half of my variation. So changing to a different principal component didn't really help my separation here. And if I had the time, I'd go through all of my different combinations of principal components to see if I could find a better separation. But we don't have that kind of time today. So let's skip ahead and ask the obvious question. How do you know which principal components to use if you're going to do some of this stuff? Well, a lot of that comes down to what are the goals of your analysis? How do you plan to use it? Are you planning to just reduce the number of dimensions and you want to contain as much variation as possible? In that case, you'd want to go with your first two principal components to try to retain as much of that total variation. But if your goal is to separate out groups, well, then you're going to have to explore your different principal components until you find those components that do the best at pulling apart the different groups that you're plotting out, in this case in colors, my delta smell life cycle model regions. And there are other ways to help provide a more analytical approach to picking components, especially in the sense of maybe separating out groups. You can plot out ellipses that contain 95% of the points. You could test how well these groups are separating using linear regression. And ANOVA is a good way to test this. You just like earlier, you could have your factors as your independent variables, and you could use your first principal component as your response variable. Or in a MANOVA, you can include multiple principal components. So here you're following up a multivariate analysis with another multivariate analysis. Of course, you could try a completely different approach entirely and use NMDS, where you can constrain the number of dimensions. Or if your goal is really to separate out groups, use an analysis that is designed to help you do that. The discriminant function analysis, unlike DCA, will build axes that maximize the separation among your groups. So it's going to pull in the variability that helps separate groups. So as I alluded to before, you can use your principal components for further analysis. So maybe our goal wasn't to separate groups. Maybe it was just to bring in as much of that variance as possible and reduce the number of dimensions. That can make it good for linear regression, especially if we have a small data set. But use caution with that. New axes, your new principal components may not always represent the same relationships as original variables. So when you pick out components, you need to be careful with your interpretations of them. Also use good judgment when you're combining variables. You don't want to encourage anyone to simply go into the data set, throw everything into an ordination analysis and see what happens. Think about what you're adding to it. And of course, if you need additional help, you're always welcome to contact me with the email address written at the bottom of the screen here, or in the R scripts, or in the worksheet that is accompanying all these materials. So thank you for sticking around and listening to me, and I hope you enjoy the rest of your workshop.
All right, thank you, Tim. Unfortunately, we do not have a ton of time because we are scheduled to go on a break in about a minute. Regardless, I don't see any questions in the chat or any hands raised. If any questions do come up, again, join us for the open Q&A. Before we go on our break, really quickly, I do want to note, however, that the data files at our website come in 4 forms. One is a CSV file where you can either right-click and download and save as a CSV, or you can save it as an HTML, copy and paste the data you see, and then use text to columns to convert that into a comma separated file. They come as an RDS or an RData file. Both of those two are file types that are specific to R. If you see that, just open the script and the script will tell you how to use it. And then the final is that I think Sam uses data that's actually in a package itself. So there is no data set. The data is actually uploaded through the code. So with that, we're going to take a 10-minute break, and please come back and join us at 10:20 where we start our next session, which is going to be regression in R.